Hey everyone, and welcome. On behalf of Forge College, I am super excited to be your host for today's Explainer, where we'll be tackling testing entry points locally. Now, if you were with us for our last lesson on entry point structure in Rust, you know we successfully built the anatomy of our Solana program. We got our entry point set up, taking in the program ID, the accounts, the instruction data, all that good stuff. But here's the thing. Writing a great entry point is really only half the battle. Today, we're going to build your personal developer's workshop. Because let's face it, testing on a live blockchain is stressful, and frankly, we all just need a safe, controlled place to break things. So let's dive right in. You know, there's a saying around Web3 that deploying untested code to a live validator is really just a very, very expensive way to find a typo. And we've all been there, right? That absolute universal dread when you push code directly to production, cross your fingers, and just pray the transaction logs don't light up with a wall of bright red error messages. Finding a bug by deploying to a live Solana validator is a slow, costly, and honestly painful feedback loop. We desperately need a local, simulated environment where we can just break things for free in milliseconds. So here's our game plan to get us there. We're going to start by defining what this developer's workshop actually looks like. Then we'll gather our tools to build a robust test harness. From there, we'll bench test our logic with lightning-fast unit tests before taking it out to the test track for full integration testing. Finally, we'll go over a solid diagnostic checklist for debugging the inevitable failures so you're completely ready to write real, bulletproof logic. All right, let's jump right into part one and figure out exactly what this local test harness is all about. Think of your local test harness as your personal engineering workbench. It's a simulated environment where you hold literally all the variables. You're calling your program's entry function, but instead of dealing with real-world, highly unpredictable blockchain traffic, you're passing in completely controlled inputs. We're talking mocked account data and highly specific instruction bytes. Doing this allows you to observe deterministic behavior. Now, deterministic is the magic word here. It just means that if you put the exact same inputs in, you're going to get the exact same results out every single time. It completely bypasses the need for a live validator network. Because let's be real, relying on mainnet traffic to test if your basic math works is a terrible idea. Okay, so how do we actually construct this workbench? Let's open up the toolbox and gather what we need. Bringing the right dependencies into your Rust project is step number one. Inside your cargo.toml file, right under dev dependencies, you're going to need a few essentials. First up is solana-program-test. This is your heavy lifter. It actually provides the simulated in-memory runtime. Next, you need Solana SDK, which gives us the core Solana data structures, things like public keys and transactions. And lastly, we want Anyhow, which is just a fantastic, flexible utility for handling errors cleanly during testing. Think of these three crates as the wrenches and screwdrivers you absolutely must have on hand. Next up, we really need to organize our workspace. You want a clean, efficient tool pegboard, right? In our Rust project, that translates to a very specific three-part file structure. First, your src/lib.rs file. This is where your main processor function lives, but we'll also tuck our lightning-fast unit tests in here. Second, you want a totally separate tests/entrytests.rs file. This is your integration testing ground, where the simulated runtime actually lives. And finally, src/test_helpers.rs. This is a dedicated spot for your helper functions. Think of them as little factories that automatically construct dummy account info and deterministic keys for you. Keep this organized, and I promise your testing life becomes so much easier. With the tools in place, let's talk about bench testing the engine using fast unit tests. So, we essentially have two distinct testing phases, and it's important to clearly contrast them. Unit tests are like literally taking the engine block completely out of the car and running it directly on a test bench. You make direct calls to your processor or function using mocked accounts. It is perfectly isolated, which makes it ideal for checking things like, does my parsing logic actually work? Or does this specific permission check fail when it's supposed to? Integration tests, on the other hand, are like dropping that engine back into the car chassis. Here, we fire up the solana-program-test runtime, we build full transactions, sign them, and test the entire end-to-end state transition. For those unit tests, we rely on the absolute classic pattern: arrange, act, assert. First, arrange. This is where you build out unique public keys and construct your mocked AccountInfo arrays. Next, you act. You just call your exported process instruction function directly, passing in those mocked arrays and some raw instruction bytes. Finally, you assert. You verify the program result that comes bouncing back, or you check if the dummy account data was actually mutated the way you expected. It's a highly controlled, tightly scoped little loop. Now, take a look at this schematic. Notice how we are completely bypassing the entire concept of a transaction here. We take raw dummy account info parts and wire them directly into the processor. To make this run smoothly, it is incredibly important that you create test-only helper functions that spit out exact byte variants for your custom instruction enums. If your main program expects an instruction to be serialized via Borscht, well, your helper function better serialize your test data using Borscht perfectly. Otherwise, the processor won't be able to deserialize it just as if it had come in from the actual network. And the payoff for this setup? Less than 100 milliseconds. That is your ultimate goal. Because you aren't spinning up a simulated blockchain or doing the heavy lifting of serializing full transactions, your feedback loop should be virtually instantaneous. If you change your line of code, you should know within a fraction of a second if you just broke your parsing logic. That kind of speed is absolutely essential to keep you in that smooth development flow state. But eventually, we have to put the car on the track. Let's move into the reality of integration testing. When we shift gears to integration testing, we use a very specific 4-step pipeline. First up, you register a program test instance and explicitly tell it to load your compiled program. Second, you start up the simulated runtime, which hands you back something called a banks client. This is basically your direct gateway to interact with the test environment. Third, you construct a real Solana instruction, pack it into a transaction, and actually sign it with a test payer key pair. Finally, step 4, you submit that transaction to the bank's client to be processed, and then you assert the final state of the accounts to prove the transaction actually did what it was supposed to do. This brings us to an absolutely crucial rule of test isolation: ephemeral accounts. You should never, ever hardcode real mainnet or devnet public keys into your tests. Why? Because your tests need to be completely independent and parallelizable. If 2 tests run at the same time and try to mutate the exact same static account state, you are going to get flaky, unpredictable failures that will drive you crazy. Instead, always rely on deterministic ephemeral accounts. Just use pubkey.newUnique to generate fresh, throwaway keys for every single test run. That guarantees you have a pristine, clean environment every time. Okay, reality check. Things will go wrong. Let's talk about diagnosing the sputters and debugging those inevitable failures. Let's be totally honest with each other here. Your tests are going to fail. A lot. But when your terminal fills with a wall of red text, do not panic. Just follow this diagnostic checklist. First, actually read the failure message closely. You need to know, did the program panic from a bad unwrap, or did it elegantly return a controlled program error? Second, run that specific failing test locally using the flag --no capture. This tells Cargo to print out all your standard output, meaning you can scatter print statements throughout your code to see intermediate states. Third, inspect the specific program error that was returned. And finally, validate your account serialization. Make absolutely sure the bytes you are packing into the test actually match how the program expects to unpack them. Speaking of things going wrong, I want to point out 2 massive beginner pitfalls you need to watch out for. The first is uninitialized account data. When you construct a dummy AccountInfo in a unit test, you have to pre-fill its data vector with the exact expected size. If you don't, your deserializer is just going to panic immediately. The second pitfall is the dreaded wrong program owner mismatch. If your program tries to mutate an account, it must explicitly own that account. If your test helper mocked the account with the wrong owner ID, the simulated runtime is going to reject that transaction completely out of hand. And that brings us to the final stage, getting ready for the real logic. Let's quickly summarize the core principles of your shiny new testing infrastructure so you can walk away today with some actionable best practices. Number 1, always use deterministic ephemeral keys to keep every single test repeatable, clean, and isolated. Number 2, lean heavily on direct, fast unit tests to validate your parsing and your early exit permission logic. You want to keep those feedback loops well under 100 milliseconds. And number 3, use the program test integration harness to confidently assert real transaction-level behavior and account mutations. So, I leave you with this final thought. Is your workshop ready for the real logic? Because honestly, now that you have this powerful safety net in place, you can start coding with absolute confidence. In our next explainer, Building Entry Logic with Rust Libraries, we are going to take this exact test foundation we just built, use it to integrate some common helper crates, and really level up our program's architecture. Thank you so much for joining me today. Remember, to learn more about this subject and to explore a massive wealth of other fantastic Web3 contents, head on over to forge.college. Keep building, keep testing, and I will see you in the next explainer.